Okay, good morning to all. Welcome back. Last class we have discussed about the resource allocation graph. Today I am going to discuss again that resource allocation graph in the last class. We have already discussed what are the vertices, what are the A's, and number of process, what are the resource figure. So in today's class, the resource allocation graph shown in below figure has the following situation. The set P, R and E. P is the process, R is the resource, and E is the age. For P, P1, P2, P3, the three resources. R1 is for R1, R2, R3 and R4 are the four resources. And E is for the A's, P1 to R1, P2 to R3 and R1 to P2 and P2 to R2 to P2 and R2 to P1 and R3 to P2. The resource instance are resource R1 has one instance, R2 having two instances, and R3 has one instance, and R4 has three instances. So here, as last discussion, that directed is from P1 to RS, that means it's called request S, and from resource to P is called assign S. Here P1 to R1, that is the request, and R1 to P2 is already assigned. That means P1 send a request to the instance of R1, but in the here the P2 holds the instance of the R1. So the resource R3 has one instance and resource R4 has three instances. The process states are process P1 is holding an instance of R2 and waiting for an instance of R1. And process P2 is holding an instance of R1 and R2 and waiting for an instance R3. Similarly, process P3 is holding an instance of R3. So the following example shows the resource allocation graph with a deadlock P1 to R1 and R1 to P2, P2 to R3, R3 to P3, P3 to R2, R2 to P1. So this is the circular, right? Now circular, there is a condition, is known as a circular wave, so it becomes a circle. So that means it is the deadlock situation. Again another case P2 to R3, R3 to P3, P3 to R2 and R2 to P1, right? So this is one type of circular waiting space. So it is a condition of the deadlock. So next is your methods of deadlock handling. The problem of deadlock can deal with the following three ways. We can use a protocol to prevent or avoid deadlock, ensuring that the system will never enter to a deadlock state. We can allow the system to enter a deadlock state, detect it and recover. So we can ignore the problem together. Deadlock prevention is a set of methods for ensuring that at least one of these necessary conditions cannot be pulled. First is the mutual exclusion. A mutual exclusion condition holds for non-shareable, and the example is a printer cannot be simultaneously shared by several processes. Or shareable resources do not require mutual exclusive access, and thus cannot be involved in a deadlock. And the example is read-only files which are in sharing condition. If several processes attempt to open the read-only file at the same time, then can be guaranteed simultaneous process. Next is your hold and wait. To ensure that the hold and wait condition never occurs in the system, we must guarantee that whenever a process requests a resource, it does not hold any other resources. To ensure that the hold by any other resources, and there are two protocols to handle this problem, such as one protocol that can be used requires each process to request and be allocated all its resources before it begins execution. The other protocol allows a process to request resource only when the process has no resource. And these protocols have two main disadvantages also. First, resource utilization may be low, and since many of the resource may be allocated but unused for a long period. Second is starvation is possible. A process that needs several popular resources may have to wait indefinitely because at least one of the resource that it needs is always allocated to some other process. So in such a summary, that in the hold and wait process, that means when one process sends a request to for a particular instance of a resource, it should not be held by other process. In that condition, the deadlock may be appear or may be happen. Next is of no preemption. To ensure that this condition does not hold, the protocol is used. If a process is holding some resource and requests another resource that cannot be immediately allocated to it, the printed one added to a list of resources for which the process is waiting. The process will restart only when it can regain its old resource as well as the new ones that it is requesting. So alternatively, if a process requests some resource, we first check whether they are available. If they are, we allocate them. If they are not available, we check whether they are allocated to some other process that is waiting for additional resources. If so, we print the desired resource from the waiting process and allocate them to the requesting process. If the resources are not either available or held by waiting process, the request process must wait. So that is the no preemption. Next, come to the circular wait. We can ensure that this condition never holds by ordering of all resources, the resource type, and to require that each process requests resource in an increasing order of enumeration. Let R equal to R1, R2, Rn be the set of resource types. We assign to each resource type a unique integer number. This allows us to compare two resources and to determine whether one precedes another in our ordering. Formally, we define a one-to-one function Rn, R and n, where n is the set of natural numbers. For example, if the set of resource type R includes step drives, disk drives, and printers, then the function f might be defined as f step drive equal to 1, f disk drive equal to 5, f equal printer equal to 12. So this is all about for today's class. From tomorrow discuss about the another topic, deadlock avoidance. Thank you for